Okay, today we are going to look at multiplying binomials with algebra tiles. But first, let's review our context from last class. We graphed f of x equals -2, x minus 2 squared plus 2. And so if we want to focus on this graph, we know our vertex is at 2, 2. We're opening down because our a is negative, and we are skinnier than normal. So from our vertex to the right 1, down 2, back to your vertex to the right 2, and down 8, which will just be one step off of our grid here. And then mirror image that to the left, and we would have a parabola that looks something like this. Now, what we talked about last class is looking at these key features. What's important to us if this were, say, to be the trajectory of a missile, then what would we know about that missile? We would know that its highest point, that maximum, would be located at 2, 2. Now, hard to say what our interval of time is for that 2. Maybe it's seconds, minutes, hours, or days. We don't know. Same thing with our y. We're not quite sure what this distance is being measured in. Maybe it's 2 meters, maybe it's 2 kilometers. Maybe it's in thousands of miles or hundreds of thousands of miles. Not quite sure. But if we had that context of our missile and we're looking at its trajectory, height and distance over time, then we would be able to give some clear depiction. But for now, let's just focus on what would be important. Another thing that would be important to us is how long this missile is actually in the air. Now we know that this, our x-axis, would be ground level, so that's our grass, looking at x-intercepts or zeros located at 1, 0, and then another one here at 2, 0. 3, 0. And so that would tell us that our missile is in the air above the ground, positive behavior, for an interval of 2 units of time. Now that also tells us that this y-intercept here at 0, -6 tells us that our missile launched from underground. And then once it hit the ground again at time 3, looks as though it has returned underground. I don't know, maybe we would have a restricted domain if our missile were in context. But here are some of the key points that we see from our graph that we can easily tell from vertex form. In vertex form, we have our maximum or minimum value, our vertex at HK. We also, from that, since we know our direction of opening and our width, that would allow us to graph this function very easily and be able to find those zeros graphically, as well as find that y-intercept graphically. Now, if we were going to compare that to our other two forms, just like with linear functions, where we had 3 forms, we have 3 different forms for a quadratic function as well. Thus far, we only know all there is to know about vertex form. Standard form and intercept form are 2 other options, and as we look at standard form, some things that we noticed in our last class is that there aren't any parentheses, whereas vertex and intercept form both contain parentheses. Vertex only contains 1 set, intercept form contains 2 sets of parentheses. We also talked about how vertex form only has 1 variable x, whereas here in standard form we see an x squared and an x. but in intercept form we see 2 individual x's. So those are just some of the highlights that we noticed from our last chat together. Now what I'm curious about is what we were picking up on from our Desmos lab is that this a in vertex form is -2. We see that a again in standard form, and we see it still in intercept form. A is always A. Now what I'm super curious about is, do we recognize any of the other numbers that we see? Like for instance, we know in vertex form that this value of 2 and 2 comes from the vertex that's part of our graph. Now when I look at standard form, I'm focused on that 8x, and I'm wondering if I have the number 8 anywhere as a key feature on my graph, and I don't. So that's interesting. I notice that my constant here from my equation, -6, I see that as my y-intercept. And some of you discovered that on your Desmos lab as well when we were checking to see if those basketballs were going to make it in the hoop or not. Okay, so that takes care of everything in standard form except for the 8. And then in intercept form, I wonder if we recognize these numbers, -1 and -3, just the opposite of our zeros, our x-intercepts. So those are some pieces to look at. If we are in vertex form, what do we know? If we're in vertex form, we know our width from our A. We know if we open up or down. And we also, of course, know our vertex. That's the name. Now, if we are in standard form, we still know the width. A is always A. And we still know if our graph opens up or down. But now we also see that we know in standard form, we know our y-intercept. This graph is crossing the y-axis at -6. Okay, for intercept form, we still know our width. And we know if our parabola opens up or down. A is always A. Doesn't matter what form we're in, we're always going to be able to determine that direction of opening and whether we are normal, fat, or skinny for our width. Now what we do see here is that in intercept form, we also are able to immediately see our zeros, also known as roots or solutions or x-intercepts. So x-intercepts, intercept form, a little bit different than slope-intercept form with lines when we were immediately being able to spy our y-intercept. So different forms provide us with different features immediately. Now, which one do we love the most? Probably we love vertex form because that's what we already know. And from vertex form, we can create a graph and quickly see all of these features. And so what we're going to spend Unit 8 looking at is these other forms that we have, standard form and intercept form, and how can we find what we want to know. Maybe we only care about how long this missile is in the air, then we just need to know the x-intercepts, and intercept form would serve us well. Maybe we just want to know where in the world this missile is launching from. How far underground is it located? And so for that reason, we would just want standard form. There wouldn't be a need for anything else if that's all we cared about. So different forms bring us different pieces of information. What we're going to focus on today is this question that we had in our last class, from vertex form to standard form. How in the world would we make that happen? Because we notice we have parentheses in vertex form, right? Parentheses squared, and we don't have any parentheses in standard form. And so what do we do to remove parentheses? And we know from our past experience that we're going to have to do some multiplying. And so in order to make that happen, we're going to need to be able to multiply more than just one term through a set of parentheses, but we're going to be able to need multiplying two terms known as binomials. And so that's really what we're focused on today. And in order to multiply binomials, we're going to use our algebra tiles. So you should have a set of algebra tiles available to you. And let's look at our different pieces. You have three different shapes and sizes. We have a large square that's blue on one side, red on the other. And it has a length of x and a width that is also x. So we would say this area on the inside of our square is x times x, or length times width, x squared. And then you should have a skinny rectangle, and you'll notice that the length of that rectangle is going to be 1, where its width is going to match your large square exactly as x. And so we would say the area of this is length times width, or 1 times x. So the area of your rectangle is x. Okay, and then you should have a teeny tiny itty bitty square that's yellow on one side and red on the other. And it has dimensions. You'll notice it matches up with that length of your rectangle, and your width is identical. That's what makes it a square. And so 1 times 1 would give us an area of 1 for that itty bitty square. Now, what's different is that you'll notice each of those colors are going to represent positive. The blue for the large square represents a positive x squared, where the red would show you that you have an area that's a negative x squared. Now, we know we can't have a negative area, just like we can't run a negative number of miles. But in projectile motion, our positive and negative is going to indicate whether we are talking direction. So are we increasing? Are we decreasing? Are we opening up? Are we opening down? So things like that direction will come into play when we're talking those negatives, even though it's technically not a negative area. So likewise, your green rectangle has an area of x. If you flip it over to the other side, then we'll say that that is negative x. And for your constant, your itty bitty square that's yellow on one side, that's a positive 1. If you flip it over to the other side, that's going to be the value of negative 1. Okay, so we have our large square, our rectangle, and our itty bitty square. And that's what we will be working with in order to multiply. So you should have a record sheet that will allow you to do some geometric discoveries here and some multiplying. We're actually going to hop to number 3 as our sample, x plus 1 times x minus 3. So if you will dump out your tiles and go ahead and set yourself up a grid with your expo marker on your table so that you can have that little t-chart as well. I'm going to pull up our app here. And we said we were going to do x plus 1. Ooh, let me double check. Yes, x plus 1 times x minus 3. And so grab a green x. I'm going to turn mine around here. So I've got my x plus 1 and my x minus 3. And so those are the length and width of what will be a rectangle, since they're not the same size. And I want to find the area, so I'm going to have to multiply. And that means I need to line up my shapes that match in size. So x times x, that gives me my x squared. And then x times a positive 1, this x, times my positive 1 would give me 1x. And then if I do a negative 1 times x, that would give me a negative x. And then negative 1 times x would be another negative x. And last one, negative 1 times x would be a negative x. And then I'm doing negative 1 times positive 1. Negative times a positive is a negative. Both of those have a 1 by 1 width there, so I can fill in the rest of my grid. So now this tells me that my area would be x squared plus 1x minus 3x and then minus 3. Now, we could combine a positive 1 and a negative 1. Those two would be 0. And so I'd only have 2x remaining. Okay? So that's what we want to do. We want to line up our factors, x minus 3 times x plus 1, and then go ahead and line up your shapes to fill in that area. You're always starting with your largest shape in the top left corner and working your way out and down from there. So let's go back to your record sheet. And let's see, this is what we had here. This was our x plus 1, and this was our x minus 3, and that gave us x squared plus 1x minus 3x minus 3. So total, that would give me f of x is equal to x squared minus 2x minus 3. Okay, so what I want you to do is to go ahead and record that on your record sheet. You can make the dimensions whatever you want. I tend to go 1, 2, 3, 4, I think is what I did. 4 spaces for my x. And then just one space for my itty bitty squares. So a positive 1, and then I had my negative 1s all lined up. Now, it doesn't have to be a work of art. I'll have my 4 by 4 for my x squared piece. Positive times positive is positive. So there's my positive x. Negative times a positive is negative. So I'll have 3 negative x's here. And if you want to label them individually or as a group, that's up to you. And then negative times a positive is negative for my itty bitty squares. So negative 1, 3 times. Now, my product, when I combine like terms, I don't have any other x squareds. Oops, forgot my f of x. F of x is equal to x squared. A positive 1 with a negative 3 would be a negative 2x. And then negative 3. Okay, so that's all you need to do is to kind of show what you have with your tiles. Tell me if your area is the area of a square or a rectangle. Since our dimensions aren't the same size, we definitely have created a rectangle. And you're doing that for all 8 of your samples. That'll give you a wide variety of practice. And I don't want you to just go through the motions. As always, we want to be good mathematicians, and we want to see if we can find a pattern in doing this. Would you be able to, by the end, and you have an extension to check yourself and see, would you be able to multiply these two factors without using your algebra tiles? So when you get to your extension, try that. Go ahead and check with your algebra tiles and see how it goes. And then we will pick up from there.